Okay, now the preceding used the fact that the volume of this shell here, the cylindrical shell cut down through the sphere, is equal to the product of its cross-sectional area and its altitude. Okay, and that's, of course, again, cross-sectional area is the area of this ring, 2 pi r sub I star delta r multiplied by h, giving us, when we use this expression for h, this expression for the volume. Now, if the mass of the sphere is big M and the radius is big R, then the volume density is big M over 4/3 pi r cubed. And it follows then that the shell mass is just this density multiplied by this volume. So the shell mass is what? I don't think I left myself enough room, so I'm going to come down to the next line here. It's M over 4/3 pi r cubed times 2 pi r I star squared multiplied by 2 times the square root of big R squared minus little r sub I star squared. Again, I'm not making good use of the board space, but you should be able to see that. In any case, it's just this multiplied by this. Now we can do a little simplification. The 2 times the 2 is going to give us 4. Dividing by 4/3 is the same as multiplying by 3/4. The 4s will divide out, leaving us a 3. So we're going to end up with 3m. The pi's are going to divide out. Now we're going to end up with r sub I star squared. And we're going to have a big R cubed in the denominator. And then we're going to have the square root of big R squared minus r sub I star squared. So that's going to be the mass contribution of this shell. And now the moment of inertia is just going to be, okay, all the mass of this shell is very nearly at distance r sub I star from the axis through the center. And I don't know if I've even stated it, it's implicit, I think, that we're finding the moment of inertia of the sphere about an axis that goes right through the center of the sphere. So the distance of all the mass from the axis, if we have a small delta r, is going to be very near r sub I star squared. I'm sorry, the distance of all the mass from the axis is going to be r sub I star, and the moment of inertia is then going to be just the delta m sub I times r sub I star squared. So the contribution of the mass in the ith interval to the moment of inertia is going to be delta m sub I times r sub I star squared. That's an approximation, but as we take the limit, the delta r's are going to shrink to 0 and the r sub i's are just going to become r's. Well, that's a nice expression, but we need to write the whole expression here. And you see that what's going to happen is we're going to multiply the expression for delta m sub I by r sub I star squared, which is going to give us an r sub I star to the 4th power here. So we're going to have, factoring out the constants, we're going to have 3 big M over big R cubed multiplied by r I star to the 5th, to the 4th. Getting ahead of myself. We will get a 5th when we integrate, times the square root of r squared minus ri star squared. And that's actually going to give us essentially a 5th power to integrate in with. going to end up with something much like a sixth power. So our integral our moment of inertia is approximately equal to the sum of our delta I sub I contributions from I equals 1 to n, again implicitly assuming that we partition from 0 to r into n equal subintervals. And without writing the intermediate step, I'm simply going to say that that's going to approach the integral from 0 to big R of 3 big M over R cubed, which is a constant that'll factor out, times R to the fourth times the square root of big R squared minus little r squared dr. That's going to be the integral for our moment of inertia. Now I've got an error. I wrote something down carelessly. Ri star when multiplied by Ri star squared doesn't give us an Ri star to the fourth, it gives us an Ri star to the third. I was a little disturbed when I wrote that down because I knew that we were going to get a factor of 5, and the power of r that we ultimately get out of this integral has to be a fifth power, so that when divided by the third it gives us a second power, and constant should be 2/5 and all that stuff. So I'm going to, off camera, I'm going to change the fourth power here and here to what it should be, namely third power. Okay, once again, correcting the fourth powers I had here and here, simply looked over here and seemed like I saw a square, and I wasn't thinking about what I was doing clearly enough, so I wrote down fourth powers, but if we look at this, we see that these should be third powers. Now, we get this integral. Now, how do we integrate this? Okay, yeah, again, using integration technique from first year calculus, you could let little r equal big R sine theta or big R cosine theta substitution, trig substitution, typical trig substitution, and everything would work out. Now, I'll just tell you what the integral is, and you can put it into a computer algebra system, but you really ought to do that integration. You need to keep your integration to the point where it's useful to you, and that's a basic integral you should be able to do from second year calculus. I'll simply say that the integral from 0 to big R of, let's put the 3 big M over big R cubed out here. You're going to be integrating R to the third times the square root of big R squared minus little r squared dr. And I would start with, let's say, let R equal big R cosine theta, and just follow the steps, typical trigonometric substitution, and what you get is going to end up being 2/5 big M big R squared, which of course is the formula you see in page 291 of the 13th edition for the moment of inertia of a sphere. So this is the sort of thing you do calculating moments of inertia. If, as many engineering students are doing at the present, you're taking multivariable calculus, you will be doing moment integrals in multivariable calculus in 3 dimensions, 2 and 3 dimensions. The integrals will be very typical. This integral is very typical of the integrals you would do in that course as well.